All right, what's up, y'all? Today we are going to talk about two-sided tests for means and how that works with confidence intervals. And of course, I'm going to walk through an example with Darren. This is exactly in your book, and but hopefully in talking through some of the details, it's like, oh, here's what he was saying here, and then I'm going to show you how to do it on your calculator as well. So this is the example from page, I don't know, whatever in your book. You can find it if you want to. There's this pineapple company, and for them it matters. Like, are we selling big pineapples or small pineapples or what? The size of the pineapples matters. Last year, we know the mean was 31 ounces. We know that because we measured last year. We threw in the new irrigation system, and somebody's wondering, okay, we're spending a lot of money on this. Is it worth it? Are we getting bigger pineapples? Are we getting better pineapples? Whatever. And so in order to do that, because maybe they're trying to decide, are we going to do this for all of the fields on our pineapple ranch or whatever? I don't know. So they're finding out. So they take a random sample of 50 pineapples from this year's crop. And Minitab, which is a computer software, it's like having an assistant that does all the work for you. They gave this data. So, the variable was weight in ounces. N equals 50. Oh, there were 50 in the sample size. I wish they would have used a little n here, but Minitab doesn't do it that way. The mean, the average was 31.935. Hey, sweet, that's bigger than 31. I guess that's a good sign. Standard error of the mean we don't care about right now. Standard deviation, that we do care about. From our 50, they averaged 31.935, but they had this standard deviation, 2.394 ounces. The average distance from this average. The minimum was this, the first quartile was this, the median, the third quartile, and the maximum. Question A here says, hey, check if there are any outliers. We're not going to worry about that for right now. It's the 1.5 IQR method. If you want to read through the answer to part A, you can do that. But part B says, do these data suggest that the mean has changed? It doesn't ask if it has increased. It says, has it changed? Is it something different than 31? Give appropriate statistical evidence. That means let's do a hypothesis test. So scroll past the IQR method. Turns out, nope, there are no outliers. We'll tune into that in a little bit. Part B is the hypothesis test. State, plan, do, conclude. The conclude is actually part C, but state, what are we going to do? We're going to test these hypotheses. The null hypothesis is, the mean is still 31. The alternate is it's something different than 31. There could be a case where you would say, I want to check the alternate hypothesis that it's bigger than 31. That is not what we're doing right now. This question is simply, is it something different than 31? So hence the not equal sign. What was mu again? Oh yeah, it's the mean weight of all the pineapples shown this year. And we state our low, not low line. Before we even start, we're saying alpha equals 0.05. If we get a p-value below 0.05, we're going to act accordingly. So the plan portion, this has not changed. Randomness, normality, and independence. Random, it says so. Normality, let's see. Do we know about the population? No, we don't. But the sample size is bigger than 30, right? The central limit theorem says, hey, we're good here. We don't have to worry about a box plot, or we don't have to worry about outliers or skewness. The sample size is bigger than 30, so the central limit theorem kicks in. Again, central limit theorem is cool for means. It doesn't do anything for proportions, but we're in means, so that's good. Independence, we checked 50 pineapples. I don't know. We're assuming there are at least 500 in the population of this field. So we're going ahead with that. Again, with the do part of it, Darren is doing it manually, which isn't hard, but I want to show you. This sampling distribution is all the possible conceivable X bars that we could pull out of a situation in which the true mean is really 31. I would expect to get X bars around 31 a lot. I'd be shocked if I got an X bar around 36, or I'd be shocked if I got an X bar around 25. I would expect to get my X bars around 31. We got an X bar of 31.935. That's above average. How much above average? Subtract 31 to C. Divided by the standard deviation. Of course it's above average. How many standard deviations above average was it? Oh, divide by this. It says This thing right here was 2.762 standard deviations above the mean. Our sample of this was almost 3 standard deviations above the mean. This talks about how you would go to table B to find out what is this p-value. What's the chance that I would be in this tail? Since it was a not equal to, I have to take this tail or its partner over here on the low side. If this was just a greater than, I would want just this one. If it's just a less than, which wouldn't make any sense in this case because we're above, it's just this one. Since it's a not equal to, it's these two tails. So whatever this is, we would double it. Pause. Go to your calculator. Hi, calculator. How are you? Stat. Scoot over to tests. We are doing a t-test because we don't know the standard deviation from the whole population. We know the standard deviation from our sample. That means we're doing a test of these hypotheses with a standard deviation that came from the sample, so that puts us in the world of t's. You will never use a z-test. Let's be honest. The data that I know, I don't have it in a list 2 or 3 or 1 or whatever. I don't know the individual data for all 50 pineapples from the sample. I do know the summary statistics because of that stuff that was listed from Minitab. The mean for my null hypothesis was 31. I have no idea what this garbage is. That's from a different problem, I guess. Our x-bar from our sample was 31.935, and the standard deviation from our sample was 2.394. N is the sample size. In our case, it was 50. Again, you have to pick now, in the alternate hypothesis, which one of these, we want the one where we think the alternate is something not equal to 31. Not greater than or less than, just not equal to. So I go down, I tell my calculator to draw that. It gives this picture that was pretty close to Darren's picture. And it says this, 2.76. Hey, that 2.762, I think, or was it 2.76? Something like that. 2.76, almost 2.8 standard deviations above the mean. That's the test statistic. What's the chance of that happening? My calculator knows, since I told it to do not equal to, it found these two probabilities together, and that's 0.0081. We're going to have to think about, is that p-value low? And if so, what do we do with it? Remember, 0.0081. Now go back to your book. Okay, hopefully not crazy surprising that Darren did it on his calculator, and he also got 0.0081. Remember 2.762, that test statistic? His shading here shows a little bit more. It makes it look like more than it is, but got the same p-value. P equals 0.0081. My chance of pulling a sample that's that far away from what I expected is less than 1%. And if the p is low, you know what to do. If the p is low, I would reject the null hypothesis, and I would say, I have evidence that the mean is now something different than 31. I'm actually kind of inclined to think it might be higher than 31, but our test just showed I would reject the hypothesis that says it's still 31. Now I have evidence that it's something else, which is exactly what he says here. The p-value of 0.0081 is less than our alpha 0.05, so we have enough to reject the null hypothesis and conclude what's stated in the alternate. Okay, so what does that have to do with confidence intervals? Scoot down a little bit further. In Minitab, there's another thing that you can do. Minitab knows all of this statistic stuff. It says, if we did this test of that mu equals 31, or wait, maybe it's not, with these things, we would have gotten a test statistic of 2.76 and a p-value of 0.008. We got those things. And so that would have told us what to do. Minitab also knows how to calculate confidence intervals. It says the 95% confidence interval for this data is 31.255 to 32.616. I am 95% confident that the interval from 31.255 to 32.616 contains the true mean weight of our pineapples now. Is 31 in there? Nope. That would have told me I should reject the idea that the mean is still 31. I bet it's something different. The advantage of a confidence interval is it not only tells you we should reject that hypothesis that the mean is still 31, we also have some pretty good evidence. I bet it's somewhere in here. I can't say that for sure, but I have pretty good evidence that it's bigger than 31. This is what the advantage of a confidence interval. And that is almost everything from section 9.3. There will be one more video.